Hello, hi, welcome back to CS700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. Last time we talked about two ways of avoiding the restriction that only continuous functions can be computable. This is a severe restriction, but a consequence of the definition. And if you don't like that consequence, you have to change the definition. But changing the definition entails other disadvantages. For example, closer undercomposition could get lost. So let me briefly review these two methods and then proceed to the final part of the current chapter 2 on real computability, namely computability of operators. Good. So here we are. So the first method for avoiding the theorem that only continuous functions can be computable is by considering multifunctions instead of functions. That is, by dropping the axiom of functionality, that is to relax to non-extensional computation. And we've seen examples where this indeed makes the difference between computability and uncomputability. For example, the Archimedean property of the real numbers. To every real number, there exists an integer that is greater than this real number, but there is no continuous function that exhibits this property. No function can map, continuously map real numbers to integers in such a way that the integer dominates the real number, because the real numbers are connected, and a continuous function would map such a connected set to a connected image, but the image are the integers, and the only connected subset of the integers are the singletons. So any continuous such function must be constant, and the constant, of course, does not satisfy this Archimedean property. However, when resorting from function to multifunction, we've seen and we've devised an algorithm that actually computes an integer upper bound to any given real number. Only the output of that algorithm will depend not just on the real number given, but also on how the real number is given. So different encodings, the same real number can yield different outputs for the algorithm. The algorithm will violate the non-extensionality. It computes a multifunction rather than a function. The other type of method for avoiding the restriction of only continuous function being computable is by adding discrete enrichment. So let us recall some example for the second approach. First example is the fact that computable C1 functions may have uncomputable derivatives. This example to my hill we will return to frequently during today's lecture. But when the function is actually twice continuously differentiable, then we saw that its derivative is again computable, but the proof depended on knowing an upper bound to this second derivative, which exists because it's a continuous. Second derivative is continuous, and the function has a compact domain. So there exists an integer upper bound, but finding such an integer upper bound is not computable. So instead, giving an algorithm such an integer upper bound, any such upper bound, that's what makes the difference between the algorithm being able to compute the derivative of the original function or not. So that's an important example of how providing such discrete enrichment, in this case bound on the second derivative, can change between computability and uncomputability of function, in this case of the second derivative. And mathematically and information theoretically, such a bound is of course contained in the information about f, but it cannot be extracted computably for the reason I've just explained, because the space of because the dependence would be discontinuous and thus uncomputable. Second example is the computable intermediate value theorem. Our proof has revealed that in order to assert that any function, computable function, which is negative on one end and positive on the other, has not just a root, that's classic, but has a computable root, but the proof would distinguish two cases, or actually several cases. One case where the root is a dyadic rational, in which case this finite information describing that dyadic rational can be hard-coded into the algorithm. And the other case when the function does not have any dyadic rational among its roots, in which case bisection would work well. And again, in order to know which of the two cases currently applies, there's no algorithm able to determine that. It has to be provided as additional discrete information. It's discrete because it's here basically it's just two cases. It's a bit that says which of the two cases currently applies. And the third example we considered were about analytic function power series expansions. Suppose we have a computable coefficient sequence such that the power series it represents has a positive radius of convergence, which means that the limit superior of the mth root of that coefficient sequence is finite. Then classically we know that whenever we are strictly inside the radius of convergence, then there exists a bound integer without loss of generality such that the coefficient sequence exhibits this at most this rate of growth, this satisfies this bound. But again, finding such a bound is algorithmically impossible. It's even impossible to verify that, because you see this bound must, by its very definition, hold for all elements of that sequence, infinitely many, and of course no algorithm can verify that in finite time. So the only way for an algorithm to get such information is to be provided from as input, because the algorithm cannot compute such an information, although mathematically, information theoretically, it is of course included in the information about the sequence, but extracting it is not possible continuously and therefore also not computable. However, such information is actually necessary in order to determine how many terms of the infinite Taylor series to take into account in order to guarantee an approximation error 2 to the minus n. The tail of the series converges geometrically, but how fast it converges, that really depends on knowing that parameter. So only that parameter allows to really guarantee absolute error bound 2 to the minus n. This is our third example of how discrete enrichment can make the difference between computability and uncomputability. So that being said, this was the end of the, let me skip over that information. It was the end about these two methods for avoiding the sometimes so-called main theorem that only computable continuous functions can be computable. And now we proceed to the last part of the current chapter 2 on real computability, namely on computing real operators and computing real functionals, and generally speaking, higher type objects. So proceeding from computability of single real numbers by computability of real sequences and computability of real functions. Now we talk about computability of real functionals and real operators, and the difference is, of course, functions receive real numbers as argument, whereas operators and functionals receive functions as argument. And in the current lecture, we will refrain from climbing even further up the type hierarchy. So operators will be the highest type objects we consider in this course. So in order to define what it means to compute a real operator, we need to define how to encode a real function argument. And to this end, let's recall how we encoded all lower levels of the type hierarchy. Namely, to compute a real number, we defined to output a sequence of approximations from some fixed countable dense set, namely the set of dyadic rationals. Here we use that the space of real numbers is second countable, is separable, has such a countable dense subset. Then next higher type to compute a partial real function would mean to convert such a sequence of dyadic approximations as argument to a sequence of dyadic rational approximations for the value. So this is a transformation perspective on real functions. So here both input and output are sequences from this fixed countable dense set. But the Weierstrass computable Weierstrass theorem has led to an equivalent alternative conception and definition, equivalent, namely to where only output is involved, outputting a sequence of both degrees and coefficients of dyadic rational polynomials that approximate the given function up to any desired error 2 to the minus n. So this is again the conception by approximating only by output, but by a fixed, by a sequence from a fixed countable dense subset, namely the countable dense subset of dyadic rational polynomials, which you can easily confirm to be countable. So, and since both are equivalent, that suggests a way how to encode functions as arguments to operators and functionals, or more precisely, how to encode continuous functions on, let's say, a compact domain. Of course, by Weierstrass, every such continuous function with compact domain admits such a sequence of approximation. So we're just going to use that to define what it means to compute, let's say, functional from set of continuous functions on a compact domain to the real numbers. Namely, the input is now a continuous real function presented by such a sequence from this countable dense subset, namely sequence of polynomials with dyadic rational coefficients. And here again the conversion, the transformation conception of a functional arises, namely output a similar sequence of dyadic rational approximations as our other countable dense subset, namely for the real numbers. So that should be our definition to compute real functionals. And now based on that definition, we can finally state formally what we've already indicated in previously, namely as every computable function must necessarily be continuous, similarly any computable functional in this sense must necessarily be continuous with respect to the supremum norm on its arguments on its domain. So this is about computing real functionals. How about computing operators? Operators have functions both as argument and as value, not necessarily of the same arity or the same domain. So our definition for computing an operator is given a sequence of approximations to a continuous function, outputs a sequence of approximations to the value of that operator, which is again a function. So here the operator is called xi, and g is the value of that operator under the argument function f. And the output of such a computation should produce a sequence of polynomials with dyadic rational coefficients that uniformly approximate that value. So that's a reasonable definition. In particular, it's closed under composition again, so two computable operators with matching domains and codomains. If they're computable, then so is their composition. That's one of the important meta criteria for us to check whether definition is reasonable. And here again, we can prove, but I'll not do that here now, that any computable operator is continuous in this sense when the domain and codomain are equipped with the supremum norm. Good, so now what is the difference between uniform and non-uniform computability? Let me recall that for you with some example. Typical statement of non-uniform computability of a function would say that if the argument x to the function is computable, then so is the value f of x of that function. So here, the argument x is arbitrary but fixed and supposed to be computable. Stronger notion is uniform computability. Here, the argument x is not arbitrary, fixed, and computable, but here the argument x is really arbitrary, not necessarily computable. On the other hand, the argument is here given by means of some encoding that we would have to fix. I mean, in this lecture, we have fixed this. You remember the three equivalent notions. In this case, we consider sequence of dyadic rational approximations to the argument x. The important message here is that uniform computability also applies to uncomputable arguments. It's an important subtle observation, and it refers to implicitly to some way of encoding x. In this lecture, we encode x not in binary, but using dyadic rational approximations. And for this case, for the uniform computability, that's where we prove that any uniformly computable function must necessarily be continuous. On the other hand, there's the goal of this chapter is to generalize that from functions to functionals. So functions receive real number x as argument and produce a real value, and non-uniform computability of function is the way I've just said. Non-uniform computability of functional says if f is a computable function, then the value of the functional lambda of f is again a computable real number, let's say. So the hypothesis here is again of this type that the argument, which is now high type object, a function, is considered fixed but restricted to be computable. So there's no discussion or need to specify any way of encoding the function because the function is fixed, and any even discrete information about the function can be considered and hard-coded in the algorithm that computes lambda of f because f is not given as input but fixed. Whereas a uniform computability claim would say that given the function f, there's a transformation that computes, given the function f, the value lambda of f. And here we need to specify how the function is encoded and given in order for this such a claim to even make sense. So again, the uniform computability, which is a stronger notion than non-uniform, has this implicit hypothesis to only consider also uncomputable functions, and it requires specifying a way of encoding such functions, which we have just done on the previous slide. And in this uniform sense, indeed, the statement generalizes any computable function, but also any computable functional and any computable operator. Uniformly computable operator is necessarily continuous. And using that principle, we can now review our previous sophisticated counterexamples on a much simpler level. Namely, you remember that we proved, for instance, that the differentiation operator on the space of C1 of continuously differentiable functions can map computable functions to uncomputable ones. That there was a non-uniform uncomputability statement, and uniformly this is now much easier. It's also a weaker uncomputability statement, right? So non-uniform computability is weaker than uniform computability. So by contraposition, non-uniform uncomputability is a stronger statement than uniform uncomputability. And indeed, this is what we have here for differentiation. Myhill proved a non-uniform uncomputability statement with all these head functions, and a uniform would simply observe that the differentiation operator from C1 to C is discontinuous. We know that since functional analysis, and therefore cannot be uniformly computable. Similarly, uncomputability of the root function, root, well, functional, receives a function as argument and outputs a real number root as value. And again, this complicated counterexample of Ernst Becker is a strong, namely a non-uniform uncomputability claim, and a weaker uniform uncomputability claim is simply the observation that the root of function depends discontinuously on the function. Here we recall this example. Small perturbation of this function makes the root jump from one end to the other. So that's why uniform computability is stronger than non-uniform computability, but requires a way of encoding argument, in particular now for higher type, of way of encoding the function argument. And this is exactly what we have achieved in defining here on this slide. And now, having done that, we can recall our previous non-uniform computability claims and try to make them uniform. So this was uncomputability, but we did have some interesting computability claims. Among them, that the indefinite Riemann integration operator and the parametric maximization operator both map computable functions to computable functions. And observe that this is indeed a non-uniform claim, and it says more formally, fix a computable function f, then its indefinite Riemann integral is again a computable function. It's a function because it depends on the upper integration bound. Similarly, if f is a computable function, then its parametric maximum is again a computable function. It's a function, not a single real number, because its value depends on the upper bound of the maximization. Of course, we could also consider such claims, computability claims regarding the definite Riemann integration functional and the unparametric maximization functional instead of operators. But let's return to this non-uniform statement. And indeed, they both statements strengthen to uniform computability statements, namely the operators of indefinite Riemann integration and parametric maximization are computable uniformly as operators with respect to the encodings of the argument and value functions as specified here, namely by sequence of diintegrational polynomial approximation. I won't give the proof here, but yeah, the proof is actually easy once you have seen how any computable function has a computable modulus of continuity. You may recall that this is something we employed in the non-uniform proofs here, but I still owe you the proof that every computable function has a computable modulus of continuity, and the proof that this can be actually found computably from information given the function. So another kind of yeah, non-uniform claim we had previously was about arithmetic. So we saw that whenever x and y are computable real numbers, then their sum x plus y is a computable real number. Their product x times y is a computable number. And then we saw that actually the function addition that maps two real numbers to their sum is uniformly computable. And similar, the function that maps two real numbers to their product is uniformly computable. So similarly, whenever we have two computable functions, then also their sum is again a computable function. And this non-uniform claim has a uniform strengthening that says pointwise addition of function considered as an operator is a computable operator. So namely, given two functions as argument, return the pointwise addition, again a function, as value. So this is an operator from functions to functions, and similar for pointwise multiplication. And again, the proof is not hard. I leave that to you. It's basically using type conversion, currying, as you recall from previous subsections. Similarly, we've shown that computable functions are closed under composition. So whenever f and g are computable and have matching domains and codomains, then their composition is again computable. That's a non-uniform claim, and the uniform strengthening says that the operator that maps given two functions f and g return the composition of the two functions. This is an operator, and this is a computable operator, as again it's not hard to see it. And similarly for join, we proved that whenever f and g are computable functions that agree on the gluing point of their domain, then also when we glue the two functions together, that's again a computable function. Non-uniform claim only refers to computable functions, and the computable uniform strengthening still is true. There's a computable operator that maps pair of such functions that do agree on the gluing point to the function that is the common extension of both functions beyond the gluing point. Okay, so thanks to this way of encoding functions as arguments and value, we can and have now talked about uniform computability, strengthening previous non-uniform computability claims. Now let's move on to discuss computability of subsets. And here we restrict to computability of compact subsets. The reason is the following. Also observed that in the previous slide we've restricted to computability of functions and operators on spaces of continuous function, and the reason is because if the space of continuous functions on a certain set is has a cardinality of the continuum, the same cardinality as real numbers, whereas the set of all functions without continuity condition is actually has cardinality strictly larger than the set of real numbers, and therefore cannot be encoded. There's no countable then subset. It's not separable. And same here, if we consider all possible subsets, this hyperspace simply has too large cardinality to find a non-trivial notion of computability. But by restricting to compact subsets, actually also to restricting to open subsets or restricting to closed subsets works as well. These hyperspaces have same cardinality as the real numbers, cardinality of the continuum, and they admit countable dense subsets, which can be used to define encodings as by sequence of approximation. And this is what we're going to do here on this slide, but first let's recall and consider some motivation. Why would we want to consider computation of compact subsets either as arguments or as values of computation? Well, for values, one class of applications is computing fractals. Common fractals are compact subsets Like for here you see a section of the Mandelbrot set, and the Mandelbrot set is a compact subset, and being able to compute the Mandelbrot set, that's what maybe you do or have done on your computer. But let me be more rigorous here. Actually, these colors here are not strictly mathematically justified. They are artifacts, beautiful artifacts to be honest, but still they are artifacts from a popular way of computing fractals. So this is nothing really inherent to the fractal, but more, yeah, as I'd like to call it, an artifact of one common popular way of computing fractals. Other ways could give rise to different colors or not at all. What really is mathematically, that's only the black part. And this is the Mandelbrot set, and everything that is not black is outside of the Mandelbrot set and maybe arguably should have the same color, let's say white, everything outside. But is it really possible to compute the Mandelbrot set? Regarding that, what you know is actually not an algorithm, but a common heuristic. Well, that Peter Hartling has proven that the Mandelbrot is indeed computable using an entirely different algorithm, to be fair, under a hypothesis, a certain topological hypothesis, a conjecture that the Mandelbrot set is supposed, but has not yet been proven to satisfy. So computing such fractals, that's one example applications for why we want to study computability of compact subsets here as output. And the other class of applications is when compact subsets are given as input, namely, for instance, when solving partial differential equations. Partial differential equations have domains, and on the boundary of the domains, usually one has to impose a boundary condition. And some of these domains are usually compact subsets. Actually, yeah, compact closures of bounded open sets, and that's our compact subsets. And these are, of course, to be an input. These are part of the input to the solvers. When solving a partial differential equation, we have to also consider the domain, and in particular, when investigating computability of partial differential equations, natural hypothesis seems to be that the domain is a computable compact subset. So let's try to define computability of compact subsets. And actually, again, we were going to have two definitions. Recall that we had three definitions for computability of real numbers. We had three definitions for computability of real functions. And fortunately, in both cases, we were not forced to choose between the three notions, but we proved that all three notions are equivalent, which turned out to be strong mathematical evidence for these definitions to be suitable. And similarly here, but before, let me slip in some cross-promotion. There is very nice book on the computability of Julia sets, another rich family of fractals, authored by Mark Braverman and by Michael Jampolsky. Please have a look into that book. So as announced, we're now going to define computability of compact subsets for now, only of real numbers, but later in the third chapter, we're going to generalize that to compact subsets of an arbitrary suitable topological space. So let's abbreviate already now K of X for a topological space. X denotes the set of non-empty compact subsets of that space. And here are two examples. So here's a compact subset of the real line. Here's the real line. This compact subset in example consists of three intervals, disjoint intervals of different lengths. And here's another example, namely in dimension 2, compact subset of the two-dimensional Euclidean plane. And one common way of in mathematics is to identify a compact set, let's say, with its characteristic function. That applies actually to any set. can be identified with its characteristic function uniquely. But for defining computability, this is not helpful because the characteristic function is almost always discontinuous and therefore uncomputable anyway. So we don't get a non-trivial notion of computability from this approach. So characteristic functions are not suitable for all purpose here, but we can modify the definition and instead consider some related functions induced by a compact subset. And the first such related concept is the distance function, which can be considered as continuous counterpart to the characteristic function. So let's do that and define a compact set to be computable if its distance function is computable. And of course, we already have defined what it means for function to be computable. So let me remind you what is a distance function of a set. So if we have a metric space X with metric D, then and we have a subset A of X, then the distance function of that subset maps every given argument in the larger set to the distance to a closest point in the smaller set A. The distance to a closest point, the infimum, in unique, but its distance, well, may or may not be attained. So that's why we write the infimum here and not the minimum. And all two simple but important observations justify doing so in our case on compact subsets, namely on compact subsets, this infimum is guaranteed to be a minimum so that it really is attained. There exists always at least one point closest to the given argument X, at least one, in general several. That's the first nice consequence of our restriction to compact subset. And the second nice consequence is that actually when restricting to compact subsets, the distance function again uniquely characterizes the compact subset. This is not true if we consider also other kinds of subsets, maybe let's say open subsets, then it is very well possible that both an open and a compact subset, which are therefore different, but still have the same distance function. But when we restrict to, let's say, closed, or in this case, compact subsets, then if the distance functions coincide, then also the compact subsets coincide. So that's the good news and justification for considering the distance function to define computability as we've done here. But as already announced, that there's another arguably equally reasonable way of making the characteristic uncomputable discontinuous characteristic function computable, maybe by replacing it with a characteristic multifunction. So that's going to be our second definition. We call a compact set to be computable if its soft characteristic multifunction is computable. So what's that? We call that a characteristic function is discontinuous almost all the time. So what was our previous workaround to make discontinuous function computable? And one approach was to generalize this to multifunction. This is exactly what we do here. So let me show you what is the definition of the soft characteristic multifunction of a set. So we fix a subset A of the space X, metric space, and this characteristic function is 1, or let's say plus, if the argument X is in the subset A, and 0, or let's say minus, when the argument X is outside of the set A. And we say the value of the soft characteristic function is plus, not only if the argument X belongs to the set, but also if the argument is not too far from the set, in the sense that the distance function, as defined before, is less or equal to 2 to the minus n. Okay, So that's what makes it soft, not necessarily inside, but also outside, but close still gives rise to a positive answer. Whereas if the argument is far from the set, in the sense that its distance to the set is greater than 2 to the minus n minus 1, then the value of the soft characteristic function is required to be negative, minus no, basically, right? Yes and no, plus, minus, 1, 0. And you see how that generalizes and weakens, softens the characteristic function. And you also see why this is a multifunction deliberately. Otherwise, it would again be discontinuous, namely there's an overlap. Whenever the argument x has distance to the set A, which is between 2 to the minus n minus 1 and 2 to the minus n, in this range, both answers are possible, and that's the essence of having a multifunction. So let me illustrate and demonstrate that concept at our second or two-dimensional example set. First, let we fix an argument x denoting a point in, let's say, the Euclidean plane, and we fix an precision parameter n, a natural number, and draw the disk of radius 2 to the minus n around that point. This is what you see here. And whenever this disk intersects the set here in gray, then the soft characteristic multifunction returns plus. And in the second case, so this is a disk of radius 2 to the minus n. For the second case, we have a disk of half the radius, right? 2 to the minus n minus 1 means half the radius. And if this smaller disk is disjoint to the set, then the soft characteristic multifunction returns a no, a minus, a negative. Okay? And if in the intermediate case, both are feasible. So here's our example. This choice of argument x as center of this disk. Here the disk is disjoint from the set. So here the answer, the result, and the return value of the soft characteristic multifunction is negative, is a no. Here, this disk does intersect the set under consideration. Therefore, in this example, with this center in the same radius parameter n, the answer to the soft characteristic multifunction is going to be positive, yes, plus. And in this final example, actually this is the intermediate case. The larger disk, the black disk of radius 2 to the minus n intersects the set. So yes, plus is a permitted answer, whereas the smaller disk of radius 2 to the minus n minus 1, half the radius, is disjoint to the set, right? You see, this yellow, white part does not intersect the set. Therefore, minus no is also a possible answer. And actually, in this case, both are possible answers. That's the essence of being multi-valued. Okay, so now you've seen two ways of modifying the classical characteristic function, which is unsuitable to being discontinuous and therefore uncomputable anyway, modifying it in different ways to make it at least continuous and therefore possibly computable. First way, by proceeding to the continuous, namely the distance function, and the second way, by proceeding to a multifunction, the soft characteristic multifunction. And either way can be used to define computability of compact subsets. And now we're in the same situation as with real numbers and with real function. We have several reasonable definitions and are faced with the problem of choosing one of them. But again, our lucky streak actually continues. It turns out that also in this case, both definitions are actually equivalent. So we don't have to choose. And actually, this means that both definitions seem to be very reasonable. Okay, so here's for you to remind what it means to compute a function or multifunction, namely to convert a sequence of arguments to a sequence of values. And based on that, we can maybe now state and prove that both definitions A and B are actually equivalent, and even more, even better, they're uniformly equivalent, which is different from, as you recall, binary computability of single real numbers to approximating real numbers. These were non-uniformly equivalent, but here we have uniform equivalence, which is even better, as you recall. And let's prove that equivalence. And one direction of the proof is actually pretty immediate. Namely, if we can compute the distance function, then by evaluating the distance function, of course, only approximately up to error 2 to the minus n minus 1, allows us to distinguish the two cases, right? So if we know the distance function only approximately, still we can distinguish because there's this overlap, in which case, if the distance function value is actually between the two values, then we can return either value plus or minus, and that allows us to compute the soft characteristic multifunction. So this was the easy direction. For the other direction, I'm going to illustrate you the proof. So let's say we have an unknown set, and we can access its soft characteristic multifunction, and we're supposed to determine the distance of this given argument point to the set A, which is unknown. And in order to determine the distance, at least approximately, up to error 2 to the minus n in this given argument, right? We're going to check the soft characteristic multifunction at that argument with a given precision parameter 2 to the minus n minus 1 actually. And if that turns out to be positive, then by the very definition, we know that the distance of x to the set is less or equal to the minus n, and therefore we can, for instance, output 0 as approximation to the distance function, right? Because 0, the actual value is less or equal to 2 to the minus n, so 0 is a good approximation to that. However, when the soft characteristic multifunction returns minus, then we only know that within the white smaller disk there's no point of A, but there could be some point of A in the black annulus or outside, and we have no idea what is the even approximate value of the distance function. So in this case, we're going to query the soft characteristic multifunction again on our argument, which is close to the previous one, namely which has center 2 to the minus n minus 1 of the previous one. And again, if the soft characteristic multifunction returns yes, then we know that there's a point of A which has distance to x, so that the distance of x to the set A is strictly between 2 to the minus n minus 1 and 2 to the minus n by triangle inequality. So we can approximate any value in this next interval as possible value approximating the distance function. Whereas when the soft characteristic multifunction says there's no point of A also in this area, the white range, then we still don't know much about the value of the distance function. Instead, we therefore make another query to this area. And if this returns positive, then again, we know the value of the distance function is between 2 to the minus n minus 1 and 2 to the minus n. Whereas if the answer is negative, then we don't know, which makes us query this part and so on. So we basically scan the points in increasing order of distance from the given argument x, proceeding in steps of width 2 to the minus n minus 1. In high dimension, that would mean proceeding on a grid of that grid width until we find a point the first point, the closest point in A to this argument x, and how close that is, that will give our approximation to the actual distance of x to the set A up to error 2 to the minus n. And we're guaranteed to find eventually such a point while scanning the grid, because remember, we're restricting to compact non-empty subsets. That's the space here. So non-empty mean eventually, while scanning the grid, we will find such a point. Okay, that concludes the proof of equivalence, and it's a uniform proof because none of the sets are actually fixed. They can be considered as given part of the input, like the distance function given by Weierstrass polynomials as previously. However, what I would like to point out is that if you, well, we haven't defined complexity yet, but still intuitively it seems that the implication from A to B seems like a pretty efficient one. We just evaluate the distance function up to error 2 to the minus n once, and thus obtain the value of the soft characteristic multifunction, whereas the converse direction from B to A seems pretty costly, namely scanning this grid of width 2 to the minus n minus 1. And if we're unlucky, then we have to walk through large parts of that grid. And if the entire compact set has, let's say, diameter 1, then it could mean scanning through exponentially 2 to the n possible grid points before having exhausted the grid or found the point closest. So that seems like intuitively, not yet formalized, an exponential time algorithm, and raises the question of, is that necessary, or can we do better, maybe polynomial time? And I emphasize that because in the fourth chapter of this lecture, when we talk about real complexity theory, we're going to present a proof to Mark Braverman, actually, from his master thesis, that in a sense, this implication represents the complexity class NP. It is possible to perform this conversion in polynomial time if and only if P is equal to NP. So in a sense, this can be considered NP complete. But again, let me point out that we haven't defined complexity, and the notion of NP completeness and reduction that you are all familiar with, of course, only applies to discrete decision problems. So it's not even fair to use that here to write that. That's why I put it in quotes. Okay, so much for later, but to wrap things up with the current subsection, now we're in the position to study also the computability of operations on sets, on compact sets. And here we're going to, for example, consider the two Boolean operations, namely intersection and union. And that's good example operations because the union of two compact sets is indeed again a compact set, non-empty compact set. And the intersection of two compact sets is again compact set. Well, could be empty actually, so we're going to require that the intersection of the two compact sets under consideration must be again non-empty. Now we can state, using the above notions of computability, that union is non-uniformly computable. It maps to whenever A and B are computable compact subsets, then also their union is a computable compact subset. And the proof of that is now that we have proven the previous theorem, the equivalence between the both notions, we are free to choose which notion we're going to use for the proof of computability of the union. And we're going to use this soft characteristic function definition because that gives rise to the simplest proof. And the proof is simply given x and n, evaluate the soft characteristic multifunction of A, first set, and evaluate the soft characteristic function of B, the second set. And if either or both of them return yes, return plus, then also return plus. So Boolean union of two compact sets translates to Boolean disjunction of the soft characteristic multifunction, and therefore easily computable and even polynomial time computable. Things start to get more interesting when we talk about intersection. Intersection is actually uncomputable, and what I'd like to show here for now is that it is discontinuous, and leave it to later parts of the lecture maybe to show that it is also non-uniformly uncomputable. They exist compact computable sets that the intersection is again non-empty but uncomputable. That's non-uniform stronger statement, which we'll not prove here now. We will prove the weaker uniform uncomputability statement as follows. So let's consider two sets. So this blue one is our set A, compact to intervals. This is our set B, again compact to intervals. And the intersection is of course only this black part, because these two are disjoint. So it's non-empty intersection, the black part. And now let's have a look at the soft characteristic multifunction when evaluated like here towards the end of the blue interval. And when we evaluate that for the intersection, of course, then the answer will always be no, negative, because the intersection here is empty. There's nothing even close to that argument, to that point in the intersection of red and blue. Okay. However, if we now gradually move the red part so that it barely just touches and overlaps with the blue part, then there's a non-trivial overlap. So when n here is sufficiently large and x is in the center of that overlap, then actually the soft characteristic multifunction here must return plus a positive answer, because there's a point sufficiently close, namely this small black interval. But small perturbation removes that intersection again. Now the intersection here is locally empty, and the soft characteristic multifunction must switch back to a negative answer to a no. So a small infinitesimal perturbation in an informal sense, I didn't talk here about host of distance, although I could, means small perturbation have huge effect on the soft characteristic multifunction. Although it is a multifunction, that doesn't help. Still, the intersection is a discontinuous operation in this implicit topology, and therefore uncomputable. And I postpone or refer you to looking at the stronger non-uniform uncomputability claim for intersection of compact sets. Okay, so that's all about computability and uncomputability of operators, of functionals, and of compact subsets. That wraps up our chapter 2 on computability over the reals. So let me briefly review what we've discussed. We've discussed computing real numbers, lowest kind of point in the type hierarchy. We've seen three notions, reasonable notions, and we've proved them equivalent, although in our new terminology they are only non-uniformly equivalent. We've considered examples and counterexamples of computable real numbers, in particular Specker's real number as an uncomputable real number, encoding in binary the halting problem. And we've discussed Oracle computable real numbers, including the one I've just mentioned. And then we've stepped up from type hierarchy from real numbers to real sequences. We've investigated the decidability of equality and shown that it is semi-decidable. Inequality is semi-decidable, but it is not decidable. Actually, it is equivalent to the halting problem, and the question of encoding is irrelevant because our strong counterexample, well, to the Becker actually, of a sequence, computable sequence, such that only the sequence index, namely an integer, is to be given as part of the input, and to check whether, to decide whether the element of that sequence with that index is 0 or not. And this turned out to be equivalent to the halting problem. So there's no encoding issue here. It's a strong uncomputability result in this sense. Well, there are only countably many real numbers. So there exists a sequence which enumerates all computable real numbers. But we've proved that any such sequence cannot be a computable sequence, because by diagonalization, we proved that every computable sequence of real numbers must meet at least one computable real number. And we've stepped up further the type hierarchy to real functions. We've considered several notions of computing real function, static one, approximation with Weierstrass polynomials, dynamic one in terms of converting sequence of approximations to the argument to sequence of approximations to the value. We've seen that these definitions satisfy nice properties, including closure under composition, closure under restriction, closure under sequence. And if you don't like the consequence of the definition, namely that any computable function must necessarily be continuous, then you need to relinquish some other of these nice properties. So there's a trade-off between definitions and between properties and consequences of definition. So we've discussed the computable version of the Weierstrass approximation theorem. Classically, every continuous function or compact set can be uniformly approximated by polynomials, and this gave rise to the two different notions of computability of real functions, which we then proved equivalent, subject to having a computable modulus of continuity, a quantitative way of capturing qualitative and strengthening qualitative continuity. And the proof of that I still owe you, and will refer to it later when we talk about the third section of this lecture. And we've discussed uncomputability induced by certain real functions. And we've seen that even if a continuously differentiable function on the unit interval is computable, its derivative may not necessarily be computable. That was a strong non-uniform counterexample due to Myhill. And on the positive side, we saw that if the function under consideration is actually twice continuously differentiable, then its derivative is again computable. But to do that, we need an upper bound, integer upper bound, let's say, on the second derivative, which we know exists, but which has to be provided as part of discrete enrichment. We've similarly seen that the wave equation may map a computable initial condition to an uncomputable solution if and because we may have been looking at the wrong function space, namely the function space equipped with a supremum norm. What has been proven to be more suitable function space is the Sobolev space, and then the wave equation actually becomes computable. Finally, we considered the root finding problem, and we showed that this is again non-uniformly uncomputable in a very strong sense. This is a Becker function which has many roots. It's computable, it's continuous, but it does not, none of its roots are computable. On the other hand, if we strengthen the hypothesis that the function is strictly negative on one end of the interval and positive on the other, then we saw that such a function will always have a computable root. We discussed multifunctions and enrichment as two ways of avoiding the condition that only continuous functions can be computable. For multifunctions, we discussed about a general conception of restriction, where the domain it becomes smaller. It's classical restriction, but also where the codomain can become larger or both. And then we discussed example applications of such multifunctions where multifunctions arise naturally in mathematics, such as the Archimedean property, the fuzzy sign or the soft sign, the fundamental theorem of algebra. And then we discussed applications of enrichment, examples in linear algebra, where many operations turned out to be uncomputable due to discontinuity, but when provided with the rank of the matrix argument under consideration, then they become computable, where the rank itself cannot be computed, cannot be computably be extracted from the entries, the continuous entries of the matrix. So, and then we discussed similarly analytic function where we need an additional integer function on a strict subset of its domain of convergence. And finally, we've just talked about computing real operators, which involved discussing ways of encoding continuous functions. For this purpose, we use the Weierstrass approximation theorem. We discussed the difference between uniform and non-uniform computability and uncomputability. So uniform computability is stronger than non-uniform computability and involves arguments that are not necessarily computable. On the other hand, to this end, it requires agreeing and fixing on a way of encoding these not necessarily computable arguments. And finally, we talked about encoding compact subsets, two natural ways of relaxing the discontinuous and therefore truly uncomputable characteristic function. One, by considering the distance function, which is a continuous counterpart. And secondly, by considering the soft characteristic multifunction, which is again a multifunction, namely which has overlap. And there we investigated the computability and uncomputability of Boolean set operations. So that's all for today, and that's all for this very long, actually, and rich chapter 2 on computability and uncomputability over the reals. And next time we're going to generalize all these to discuss computability and uncomputability of general T0 spaces, topological spaces with very mild separation properties. Thanks you for your attention. All the best wishes and bye. See you next time.